The main focus of this video will be on the composite of field extensions. So let's say that K1 and K2 are subfields of a field K. The composite field of K1 and K2, denoted K1, K2, written right next to each other like that, is the smallest subfield of K containing both K1 and K2. Okay, so that's a composite field for two subfields, but you could take any collection of subfields and define the composite field. So the composite of any collection of subfields is the smallest subfield of K containing each field in that collection. All right, so this already relates pretty directly to stuff that we have been talking about. I want to mention exercise 6 in section 13.2, which is on homework 3. If you have K over F being an extension of fields and alpha 1 up through alpha K being in K, this bigger field, then you can take the field generated by alpha 1 up through alpha K over F. And that is a subfield of K. And it clearly contains each one of the field generated by alpha 1 over F, the field generated by alpha 2 over F, and so on. So the composite of this collection of fields is clearly a subfield of this field generated by alpha 1 up through alpha K over F. But by the definition of this field as being the smallest extension of F that contains each one of alpha 1 up through alpha K, you can show that, in fact, it is the composite of this collection of fields. So it's worth writing down like a fully rigorous argument that this really is true, because it's often going to be useful to describe composites of a bunch of field extensions in terms of the field generated over the base field by a bunch of elements. Okay, so I'll leave this to you. Our next goal is going to be to prove proposition 21, which tells us something about the degree of the composite of two fields. So let's say that K1 and K2 are finite extensions of a field K, and they're contained in some, of a field F, and they are contained in some field K. So K1 and K2 are extensions of F, and they're contained in K. Then the degree of the composite K1 and K2 over F is at most the product of the degrees, of the degree of K1 over F times the degree of K2 over F. Okay, so how are we going to think about this? Well, what is the degree of a field extension? It's the dimension of the bigger field as a vector space over the smaller field. So let's think about vector spaces. If we take alpha 1 up through alpha n to be a basis for K1 as a vector space over F, and beta 1 up through beta m as a basis for K2 as a vector space over F, then we can take the product of these elements, the alpha i's and the beta j's. Why does it even make sense to take the product of these elements? Well, K1 and K2 are both contained in some field K, and we can certainly multiply elements in K, so it's okay to do this. So in fact, not only are they both contained in K, but they're both contained in the composite K1, K2. So we have this collection of alpha I beta j times beta j, where I goes from 1 to n and j goes from 1 to m. So this is n times m elements in the composite K1, K2. And okay, alpha 1 up through alpha n, these are a basis. Beta 1 up through beta m, these are a basis. I am not claiming that this set of n times m elements is a basis for K1, K2 as a vector space over F, but it does span K1, K2 as a vector space over F. That every element of K1, K2 can be written as a linear combination of this special set of n times m elements where the coefficients are in F. Okay, so we're going to prove that. And then when does equality actually hold here? Like in this case, so if this extension has degree n, this has degree m, this is n times m over here. When is the degree of this extension actually n times m? Well, we have this spanning set of size n times m. When is it actually a basis? So equality holds in star if and only if this set beta 1 up through beta m is a linearly independent set of elements over K1. Okay, so what do we know? This is a basis for K2 over F. That means if you have any linear combination of these elements with coefficients in F, that gives you 0, then each one of those coefficients was 0. But when is it true that any linear combination of these elements with coefficients in the bigger field K1 that gives you 0 must have each one of the coefficients being 0? Okay, so there are several parts to this. I'm going to pause and erase, and we will prove this proposition. Let's start the proof of this proposition. So we're going to keep a lot of this notation where alpha 1 up through alpha n will be a basis for K1 over F. Beta 1 up through beta m will be a basis for K2 over F. So the first thing we want to do is take this composite field K1, K2 and rewrite it, noting that it's equal to the field generated by alpha 1 up through alpha n and beta 1 up through beta m over F. The idea is just to see inclusion both ways. That, okay, K1, K2 clearly contains F and all of these elements. And I'll let you think about the other containment to show that these really are equal. All right, so the idea is going to be, what do elements in this field look like? Well, this idea of taking this field generated by a whole bunch of elements over F as a sequence of simple extensions, we know that we can write every element here as polynomials with coefficients in F, where the degrees in each one of these alpha 1 up through alpha n and beta 1 up through beta m, for each different one of these terms, we have a different maximum degree, which is coming from the degree of some relative extension along the way, getting to this whole big extension here. So we definitely know we can write elements of this field as polynomials in alpha 1 up through alpha n, beta 1 up through beta m with coefficients in F. It's not so clear what the degrees of those polynomials are right now. So that's what we're going to think about. And a big first observation is, okay, you have alpha 1 up through alpha n. This is a basis for K1 as a vector space over F. Alpha 1 squared is in this field generated by alpha 1 up through alpha n over F, which is which is this K1. So alpha 1 squared is in this field. So it is in the span of this set of basis elements. So that means that you can write alpha 1 squared as a linear combination of alpha 1 up through alpha n with coefficients in F. So similarly, I mean, I just picked alpha 1 squared. You could have picked alpha I to the 6th power. If you take any power of any alpha I, you can write it as a linear combination of alpha 1 up through alpha n with coefficients in F. And we can make a totally analogous statement for beta 1 up through beta m. If you have like beta 2 to the 17th power, that is some linear combination of beta 1 up through beta m with coefficients in F. And this observation is going to allow us to see that if you take the set of all things that are aij times alpha I beta j, where I goes from 1 to n and j goes from 1 to m, so linear combinations of these n times m special elements that come from alpha I times beta j, where our aij's are in F, this set is closed under addition. That's obviously true. And it's also closed under multiplication. So it's closed under addition and multiplication. I guess I didn't organize this as well as I could have. Because what happens when you multiply things like this is you multiply two terms that look like this, and you might get something in the product, if you just distribute everything out, that has, say, like an alpha 1 cubed in it. But we know that you can take that alpha 1 cubed and you can rewrite it as a linear combination of alpha 1 up through alpha n with coefficients in F. And then you expand everything out, and you don't have that alpha 1 cubed anymore. So when you multiply, you expand everything out, and then every time you see a power of alpha I that's bigger than 1 or a power of beta j that's bigger than 1, you replace these powers with linear expressions. And the key thing is that if you take a linear expression, like alpha 1 plus alpha 2 times beta 3 plus beta 4, you get something that is a linear combination of alpha I times beta j's. So this set is closed under addition and multiplication. Okay, so what do we know? We know that elements in this field are polynomials of some degrees with coefficients in f in alpha 1 up through alpha n, beta 1 up through beta m. And what we're seeing here is that we can take any expression of that form, replace those higher powers, and write it in this form. So what we're seeing is that the n times m special elements, alpha I times beta j, span k1, k2, span this entire field generated by alpha 1 up through alpha n, beta 1 up through beta m as a vector space over f. And what does that mean? That means this dimension is at most the size of this spanning set, which is n times m. And that dimension is the degree of the field extension k1, k2 over f. So, okay, what have we proven? We've proven this first part, star. We've proven this second part about a basis here, a basis there. It gives us a spanning set for the composite. So I'm going to pause and erase, and we'll do the last piece of this, which is to characterize when equality holds and the degree of this field extension actually is n times m. Let's finish the proof of proposition 21. Where were we? We have this special set of n times m elements that span k1, k2 as a vector space over f, which means that the degree of this extension is at most n times m. Okay, so what do we know? We have this field, k1, k2, which is the field generated by alpha 1 up through alpha n and beta 1 up through beta m over f. And I'll let you think about this. This is something where it's worth writing down a full proof one time, showing containment each way, that this is the same field as taking the field generated by beta 1 up through beta m over the field generated by alpha 1 up through alpha n over f. But this field is k1. So k1, k2 is the field generated by beta 1 up through beta m over k1. All right, so what do we know? We know that beta 1 up through beta m span k1, k2 as a vector space over k1. I mean, if you just think about what the elements of k1, k2 look like, if you look at beta 1 up through beta m and you group together all the other coefficients, those coefficients are all in k1. So every element in here can be written as a k1 linear combination of beta 1 up through beta m. So what does that tell us about the degree of this extension? Well, it's the degree of this extension of k1 we get by adjoining beta 1 up through beta m, which is at most m. We have a spanning set of size m. And this m is the degree of the extension where you adjoin beta 1 up through beta m to f. So that's the degree of k2 over f. So what are we seeing? We're seeing that we have this spanning set of size m for k1, k2 over k1. And equality holds here in this product, where it's the degree of k2 over f times the degree of k1 over f, if and only if these degrees are equal. So using the multiplicativity of degrees, this degree is equal to this degree times the degree of k1 over f, which is n. So when is this equal to m? We have this spanning set of size m, and equality holds in this formula if and only if this spanning set, beta 1 up through beta m for k1, k2 over k1, is actually a basis for k1, k2 as a vector space over k1. It's definitely a spanning set, so equality holds if and only if this set of elements is a linearly independent set of elements of k1, k2 over k1, which really concretely, like every linear combination of these elements with coefficients in k1 that is equal to 0, we must have each one of those coefficients being equal to 0. So this completes the proof of this proposition that tells us something about the degree of the composite of two fields, but it's actually telling us more than that, because it's telling us something about if you have a basis for your first field as a vector space over F and a basis for your second vector space, your second field as a vector space over F, then at least you get a spanning set for the composite as a vector space over F. And it's telling you something about how to think about whether or not that spanning set is actually a basis. All right, so I'm going to pause and erase, and I'm going to give a corollary of this result that ends up being quite useful in applications, and then I'll talk about some examples. Let's prove corollary 22, which says if you have K1, a degree n extension of F, and K2, a degree m extension of F, where the GCD of n and m is 1, then the degree of the composite is equal to the product of the degrees, is n times m. So it's the same setup as proposition 21, and it's saying that when n and m are relatively prime, that's giving you one case where equality must hold. And it's easiest to see why this is true by drawing a little field diagram. We have this composite at the top, which contains each of K1 and K2 as a subfield, and we have F at the bottom. K1 is a degree n extension of F. K2 is a degree m extension of F. And we know that the composite altogether has degree at most n times m. So whatever this degree is, the degree of K1, K2 over K1, it's at most m. And whatever this degree is of K1, K2 over K2, it's at most n. And what do we know? By multiplicativity of degrees, the degree of K1, K2 over F is n times something. And it's also m times something. So what does that mean? That means n divides this degree, and m divides this degree. But that means the least common multiple of n and m has to divide the degree. And if n and m are relatively prime, that least common multiple is n times m. So n times m divides this degree, and we know this degree is at most n times m. So in fact, it is equal to n times m. So what do? We're using the multiplicativity of degrees to say that the least common multiple of n and m must divide the degree of this extension. So when you have n and m being relatively prime, you're already done. Okay, so let's look at an example where we can actually get our hands on what these composites are. So to talk about composites, you want extensions K1 and K2 of a field F that are contained in a common field K. All right, well, let's say the Q adjoin the sixth root of 2, this real positive sixth root of 2. Let's call that K. This contains both K1, Q adjoin the square root of 2, and K2, Q adjoin the cube root of 2. So just to check, to be really concrete, why? You take the sixth root of 2 and you cube it, you get square root of 2. You take the sixth root of 2 and you square it, you get the cube root of 2. So this field clearly contains each of these other two. So what does that mean? Whatever the composite of K1, K2 is, it's contained in K. It's the smallest subfield of K containing both K1 and K2. But okay, I mean, if you have a field that contains both square root of 2 and cube root of 2, it has to contain their ratio. And what is that ratio? This is square root of 2 divided by cube root of 2. This is 6 root of 2 cubed divided by 6 root of 2 squared. This is the 6 root of 2. So any field containing both K1 and K2 has to contain the 6 root of 2. So it has to contain Q adjoin the 6 root of 2. So in particular, the composite, which is a field that contains both of these elements, also contains Q adjoin the 6 root of 2. So we've shown inclusion both ways, and we see that Q adjoin the 6 root of 2 is the composite of these two fields. Okay, great. That was an example where we could work really directly with the elements to see what the composite is. But you can also use this corollary to say something. So we have K1, Q adjoin square root of 2. We have K2, Q adjoin the cube root of 2. We know that K1 has degree 2 over Q. K2 has degree 3 over Q. 2 and 3 are relatively prime. We know that the composite has degree at most 2 times 3. And in fact, because 2 and 3 are relatively prime, we see that the degree of the composite as an extension of Q is 6. That doesn't tell us what this composite is, but it's like a pretty much no effort way to see that the composite is an extension of degree 6 and not something smaller than 6. I mean, we already knew that it was degree 6 because we computed what it is. But there will be situations where it's easier to apply this kind of idea that just uses some arithmetic condition on the degrees rather than having to like get into the guts of actually working with the elements in these fields. All right, I'm going to pause and erase, and then I just want to talk very briefly about two small issues that we're not going to focus on going forward in this course. Let's suppose we have an element alpha that's algebraic over Q. What do we know? We know that if we take the field generated by alpha over Q, that's a finite extension of Q, and we know the degree is equal to the degree of the minimal polynomial of alpha over Q. And once we know that degree, we have a great description of the elements in the field generated by alpha over Q. It's polynomials in alpha of degree at most n-1 with coefficients in Q. So if we want to work with this field, it's really important that we be able to determine this minimal polynomial. So you can ask, if I just give you an element and say it is algebraic over Q, how do you find its minimal polynomial? More generally, you don't have to take Q as the base field here. If you have any field F and you have an element that's algebraic over F, how do you find the minimal polynomial of that element over F? And this was really important when we were trying to even determine the degree of the field generated by two elements, alpha and beta over F. One idea was to take a sequence of simple extensions, and we had to determine the degree of the field generated by alpha and beta over F as an extension of the field generated by alpha over F. So we needed to find the minimal degree of the minimal polynomial of beta over F adjoint alpha. So how do you do that? We saw some examples, like if you take the nth root of 2, it's easy to write down a polynomial that is monic and irreducible that this element satisfies. So once you find one polynomial, it's easy to check that it is the minimal polynomial. We saw a trickier example. We talked about like square root of 2 plus square root of 5. If you square it, subtract something, and square it again, then you can find a polynomial of degree 4 that this element satisfies. But in general, it's tricky to start with an element and write down the minimal polynomial. There are procedures for doing this, and this is actually something that's important that we talk about more in the Math 232 number theory sequence. Dummen and Foote give sort of an indication of where this begins. If you look at exercises 19 and 20 in section 13.2, it begins to address this question of how do you compute the minimal polynomial of an element over a field. And then if you want a much more systematic, thorough discussion of how to really do this, Conrad has two sets of very nice notes, trace and norm 1 and trace and norm 2. And I'll put links to those on the course website. And I encourage you to check those out. But in general, it's a little challenging, and you should not expect lots of problems in this course that are like, here's some crazy looking algebraic number, write down its minimal polynomial. So I'm going to pause and erase, and I'll talk very, very briefly about section 13.3 and just give you an outline of what is covered in this section. This is not something we'll talk about in detail in this course. I just want to talk very briefly about section 13.3 of Dummen and Foote, which is about classical straight edge and compass constructions. And the idea is that there are these three very classical problems in geometry: the problem of doubling the cube, trisecting the angle, and squaring the circle. And the question is whether you can accomplish these three geometric things via a sequence of compass and straight edge moves. So there are certain things you're allowed to do with a compass and straight edge. And what you can do is you can write down, starting from a line segment of unit length using your compass and straight edge, you can construct some other lengths. And the big idea in this section is to translate this construction of lengths by compass and straight edge into algebraic terms. So these are really neat applications of the theory of fields that we've developed so far, but I don't want to go through the geometry behind this step where you talk about like what things you're allowed to do with a compass and straightedge, what line segment lengths you can construct given this set of operations that you have. Okay, so I don't want to talk about this in general, but it's something that it's pretty neat, so you should check it out. The main proposition that you prove is if you have an element in R that starting from some field, some subfield of R, if you can get to this real number length by a series of compass and straightedge moves, constructions, then the degree of the field generated by alpha over F as a field extension of F is a power of 2. So 2 to the k for some non-negative integer k. So the idea is starting from some set of lengths that you can construct, you ask what other things can you construct, and the new lengths that you construct that were not in your field F, you're showing something very strong about the degrees of those extensions that you get. So in order to prove that this is true, you have to understand what can you do with a series of compass and straightedge constructions. And again, I don't want to get into the geometry of how this works, but it's a neat application, so please check it out. And then you show that none of these 3 geometric problems is solvable by showing that each one involves constructing a length alpha for which the degree of q adjoint alpha over q is not a power of 2. Okay, so it's a really cool thing to use the theory of fields to show that these classical geometry problems that people have thought about for thousands of years are impossible to solve given this certain set of compass and straightedge moves, these constructions that you're allowed to do. So I encourage you to check this out, especially if you find this kind of plane geometry to be interesting. So I'll point out that there's more that you could do in this direction. There is some discussion in Dumb and Foot, especially in the exercises, about, well, what happens when you move from straightedge and compass constructions to ruler and compass constructions that are a little bit different. And there's this whole neat interaction between some questions in classical geometry and the theory of fields.